Hey there, in this video I want to talk about the relaxation method for ordinary differential equations. And I'm saying for ODEs here because we've used this method before. We've done it with nonlinear equations, and we're going to do it again with partial differential equations. And it's pretty much the same technique. To get an ordinary differential equation to look like a linear equation, we're going to use the idea that a derivative can be calculated numerically as a finite difference. So just as a reminder, if we have a function f and we want to numerically calculate its derivative, we can get that approximately if we take f and evaluate it half a step ahead of the current point, subtract going backwards half a step, so this is called the midpoint rule, and divide by our small step size h. And as long as h is small enough, this will be numerically accurate. We can do the same sort of thing for second derivatives or higher order derivatives by continuing the pattern. So the second derivative would be at least approximately equal to taking the first derivative at x plus h on 2 and subtracting the first derivative at x minus h on 2 and dividing by h. Or if we make the substitution from above and rearrange it a little bit, we get a rule for second derivatives. And I'm going to write this down because second derivatives are pretty common. So we end up taking f and evaluating it one full step ahead plus x one step backwards, and then from that subtract 2 times f at its current location. And again, this final result here is just from algebra of taking these two lines up here and plugging the first into the second and rearranging. Okay, so let's set up an example. So this requires doing some calculation by hand, and then we're going to jump over to the notebook and do it numerically. So let's say that we want to do a ball undergoing free fall. Okay, so the equation for a ball falling is the second derivative of y with respect to time squared is equal to negative g. And let's say that the ball starts at y position 0 and it lands 10 seconds later. Okay, so those will be what are called boundary conditions for our problem. Okay, so coming back here to our equation, we replace the derivative with a finite difference. So this is going to be y at t plus h plus y at t minus h minus 2 times y at t. Divide that all by h squared. And now what I want to do is I want to rearrange, and I'm trying to solve here for y. Okay, so just a little bit of algebra. We end up with y is going to have to be equal to 1/2 times the quantity, y at t plus h, plus y at t minus h, all of that plus 1/2 gh squared. And the idea of the relaxation method then is if we iterate this relationship, setting y over and over and over again, updating it as we go, eventually we, or at least if we're lucky, we're going to converge on a solution. So we're going to try that out in the notebook. Okay, so here we are back in the notebook, and I've copied down the last line from our ball example. Now the next thing I want to look at is what's going on with y of t plus h, and y of t minus h. Like, what do they represent? So y here is going to be an array, and each element of the array represents a different value of time. Y at t plus h is one step ahead in the array, and y at t minus h is one step backwards in the array. So let's say that the current element of the array is 3, just to make up a number. So this would be like y of 3. Then this would be y at 4, this would be y at 2. So to illustrate that example, let's do a really simple array for y. We'll just do a straight a range of 10. It only has 10 things in it. Not only that, but we should give it some boundary conditions. So y at 0 should be the same thing as y at negative 1. Should be, I'm just going to say 0 here for our boundary conditions. Okay, and then y is the same thing as y as a function of time in the mathematical version. And so now y at t plus h, that's basically the element to the right. So let's call it right. And that's going to be equal to a sliced version of y. I'll put in the slicing in just a moment. And then we have the same kind of idea for left. That would be just leftwards. So we're going to take y and slice it. And that would give us our y at t minus h. So now what slicing should we use? Well, you might think to do something like 1 through 0, or 1 to the end, I should say, and then go all the way up to -1. And, to be fair, that's the first thing that would come to mind for me, although that's not quite the right values. So here's the issue. So the value y here is 10 long, but we only ever adjust the inner 8 elements. We never adjust the very 0th element or the very last element because those are our boundary conditions. Those cannot be changed. They're not allowed to be changed. We're only ever adjusting the middle 8. So when we do an expression like this and we calculate new values for those, we want to write this as an array expression. And so each of these right and left over here, they can only be 8 elements long. So right now, this is 9 elements long. What I really want to do is start at 2 and end at 2. That's kind of the secret sauce for doing this method here. And not only does that match the correct number of elements, but the reason you'd start at 2 is you never do this calculation, like you never try to find a point to the right of this last value here. And you never try to find a point to the left of the first value here. And so that kind of gives us like an extra, removes one extra element from these arrays. To further emphasize it, let's print out these results so that we can inspect and see that, yes, this is what we have to have. So I want to print here, it will just give us a label y at t, and then we'll just do the middle 8 elements of the array y. So this again is so that we don't change our boundary conditions. And we'll print y at t plus h. And so then we said that was going to be the array we named right. And then we'll print y at t minus h. And that would be the array we named left. And then let's make sure that these line up. I want these colons here to all be vertically aligned. So I'm going to add some extra space to this first line here. Okay, let's print them out. So the middle 8 elements would be 1 through 8. We have zeros before and after that. And now let's check. So just to the right of point 1 is 2. Okay, and that's sure enough is what this says. And just to the left of 1 was that boundary condition 0. That's what this says. Let's just do a point near here at the end. Okay, so what's to the right of the 8? It should be the boundary condition 0. So sure enough. What's to the left of the 8? It's a 7. Sure enough. Okay, so that's showing us that this was the right way to do it, that it's maybe a little counterintuitive, but we really want 2's here to be the range on these slices. So now if I wanted to write this equation up here in Python code, what would it look like? Well, what I would write there is not y equals, but a sliced version of y equals. Again, because I never want to change the boundary conditions, I don't actually include the first or last element of y. Then we have a 1/2 multiplied by y to the right, which is slicing here with a 2, plus y to the left, slicing with a -2. And then we have the final term here, 1/2 gh squared. So assuming that variables g and h have been defined for us already. That's how we would write our math in Python. All right, so let's put the full method together now. We do have to define g, just like I said a moment ago, so g is 9.8. I'm also going to want to define a t-final. I'm going to put it up here just to make it easy to change later on. But that's going to show up here in a linspace for different time values I want to use. This is basically my x-axis. So I'm going to go 0 to t-final, and we're going to take 51 steps just to match the earlier version of this example. H is going to depend on the total time and the number of steps we're taking. So that would be based on t-final divided by the number of steps. I accidentally commented that out. The number of steps here is 50. So be careful of that. We just have this seeming inconsistency here. 51 and 50. That's because we have a linspace, and this means 51 points. There's 50 steps in between those points. It's not a big difference between 50 and 51, and as we make this value larger and larger, then the difference becomes smaller and smaller, but it is a slight error that can easily creep into your code. So keep in mind the difference between points and steps in between those points. Okay, now we need some starting values for y. And it's not just a y initial, but it's a y everywhere to start with. And depending on where you start will change how long it takes to converge. I suppose if you picked really terrible values for your starting y, you may not converge at all. I'm going to go with all zeros. It's easy for one thing, and it also matches the boundary conditions. And that's important. We have to have our boundary conditions because we're never going to change them from now on. And so zeros all the way across does that for us. All right, so now we're going to set up a loop here. So we're going to do iterations until we're happy with the tolerance we've reached. So we could do this as a while loop while this condition isn't hitting our tolerance, but in principle that could run forever if things aren't working out for us. So I prefer to use a for loop with just a very large number of steps here, figuring if this doesn't work after 1,000,000 steps, it's not going to work, and I'd rather my code print an error message than just sit there forever. Okay, so now in here, there's another important line we need to do. We need to make sure that we are stashing an old value of the array because we're going to do a tolerance check. Basically, we're going to check if y minus y last is less than some tolerance. And when we stash it, we don't want to say y last equals y. Okay, the reason we don't want to do that is because that makes them identical. And when I change y, I also change y last. And then when I subtract them, I'm going to guaranteed get 0. And it's going to say, oh, you have perfect accuracy, which is not at all true. The correct way to do this is y last is a copy of y. Okay, and so that protects you from a seemingly insane bug. That's really just because of the way Python works. We talked about this ages ago, but with complex things like lists or arrays, this name just points to some portion of the computer's memory. And a statement like this says, make y last reference the same thing that y does. And so that makes them actually the same thing. Okay, so now we can use this line we typed up here. And this is our actual relaxation method. Change the middle points in y based on looking to the right and to the left. And then we're going to add on this change here. This last part is why we don't stay at 0 forever. And so that's why this will work out for us. And now we check to see if we have converged. So if the maximum value of the absolute value of the difference between the two y and y lasts is less than, let's make up something, let's just say 1 part in 1,000,000. This depends on, you know, what your application is here, but that feels like a good result to me. So if it's less than 1,000,000, then we have our solution. I'm curious, how long does this take? So let's just print out a message. So solution converged after I plus 1 steps. And then we're going to get out of our for loop because hopefully this number is nowhere near 1,000,000. But suppose the number does reach 1,000,000, then we can attach an else statement to our for loop to let us know what happened. Instead of just quietly returning with nothing there, it's a good idea to have some kind of feedback, at least when developing your code, at least. So we're going to say solution failed to converge. All right, let's see if this runs. Invalid syntax, yeah, because I left out the word in for I in range. It's been a while since I made a for loop. All right, so solution converged after 6,294 steps. Okay, yeah, that's definitely less than 1,000,000. And now we can check out to see what it looks like. So let's plot t and y. We'll do discrete points because there's only 51 of them. And what we're looking here for is that nice parabola shape. Okay, sure enough, we got it. And so we've solved our problem. We've used our relaxation method, and we've applied it to the thrown ball example. And so this just iterates and the solution eventually takes the shape. Now, for the sake of illustration, I think it's kind of neat to look at how we get to this shape. Like, what does it look like at each time step? So I'm going to make a few tiny changes here. What I'm going to do is I want to stash y at each of these iterations, and then I want to graph at least some subset of them. Or, you know what, actually, let's animate some subset of them. Okay, so let's call this history of y, and it's going to be a list of values as we go. And we're going to append them. We can do that anywhere. Let's do it here. So history of y dot append. Let's make this a y copy, just to be safe. We don't want to append y because y changes, and we're going to find that every picture looks exactly the same as the last one. But appending a copy here would be safe for us. Okay, and so that's going to give me a list with 6,294 things in it. I don't want to animate that much stuff, so you know, I feel like we should trim that by some factor. But let's make our animation code here. So we're going to do plot.figure, and then I want some kind of line to update. This comma here at the end is because plot likes to return a list of things, and so I can tuple and pack a list that has one thing in it, put it into line. Okay, and we want to do dots so it looks like the other graph. We want to make sure we set our x limits and y limits so that we don't rescale as we go. I think that's more important for the y limits. The x limits should always be the same, but the y limits, if left alone, would keep scaling and make things harder to interpret. Okay, we'll make some kind of animation function, and then in this case, there's not really much to it. We just want to set the line to some value that we stashed in history of y. Okay, now if we just do this, it's going to do like 6,000 of them. So let's create a variable called skip, which is basically how many do I want to skip. And let's start with skip as 100. So that would give me 62 plots. I mean, that's going to run pretty quickly. Okay, and the idea here is then, so if skip's 100, when frame is 0, this will be the first thing. When frame is 1, it's going to look all the way up to element 100. When frame was 2, it's going to look at element 200. And so basically skipping every 100th. All right, now the rest of this is just boiler code and boiler code. Yeah, let's call it boiler code, boilerplate code. So I think I've already imported func animation. Yeah, I did. Fig and animate, and the number of frames is equal to, we said 62. A better way to do this would be to just calculate it in case I want to change my mind, and I might if we want to see if this animation is running too quickly. So I'm going to take the length of the history of y and then divide it by skip. Double slash here is integer division because I can't have a floating point number for my total number of frames. So this does the division and then rounds down. And then finally, my favorite interval is 20, but we'll adjust if we really have to. Okay, so then we're going to do something like anim to HTML5, something like that. Not auto-completing to me. For me, all right, HTML5, I think it's HTML5 video. And HTML, I already have display imported, I think, so let's see if that cab completes. Yep, HTML of video, and then display.display the HTML. Finally, we're going to do a plot.close so we don't get an extra figure. All right, so I mean, I really wish they made this easier to use. I have to write all these extra lines. But this should animate it, at least in some way. History of y is not defined. Is that because I never ran the cell again? That might be. Okay, it seems to be working now. Didn't take too long. Okay, there we go. And so for illustration's sake, we can see this thing just sort of pop up. Maybe we don't want to skip so many. Like, let's go with skip is 20. And the nice thing about making a variable for this is I don't have to change any other stuff in my code. So we'll just pause here for a moment until it shows up. Okay, and here is our final animation, a little bit slower this time. And we can see that it actually very quickly gets this shape mostly right, and it spends most of the time and most of the iterations getting us to that final tolerance of 1 part in a million. So if we set our tolerance lower, this would converge much quicker. It would also be a little bit less accurate. That's the price you pay, but you can see that the relaxation method actually worked really well here for this particular equation.